In part A of the problem, we're given this wave function, and it looks like it's a superposition of two different states of the simple harmonic oscillator, one at the ground state and one at the first excited state. And our mission for this part of the problem is just to find the normalization constant 8. Now, before we get into the actual big part of it, I want to show you a quick shortcut, what you can do with this stuff moving forward. So the whole point of the normalization constant is to, well, normalize these two states so that whenever you take the magnitude squared of each state, the probability density, the probability of finding each state, when you add them all up, all becomes 1. And so when we know that we have a superposition of these two states, whenever we add up the probability, it has to be equal to 1 or 100%. So that means that the probability has to be 1 whenever you do the square magnitude of both of these together. When you add up the probability, these are the probabilities of each state. So this is the probability of ground state, and this is the probability of the first excited state. Anyways, as you can see, this is a relatively easy algebra problem to solve for. You take the a out here, the a squared, and then now you have a 9 plus 16, which is the 4 and the 3 squared. Excuse me. Let me move this. No big deal. It's equal to 1. And then whenever you solve for a will eventually become, let's go ahead and move this over here. And this one too, why not? Should have just moved them both, but that's okay. So now whenever you solve for a is going to be equal to the square root of 1 over 25, which is equal to 1 over 5. So that's a really quick way to do it. All you really have to do is see what, if it's a superposition of two states and the normalization constant is shared between these two states, that normalization constant is just going to be a division factor. So whenever you do the square magnitude of both of them, the sum becomes 1. But now when you have that quick way, let's do it the more rigorous way where it highlights some more parts of the physics. So whenever we take the integral of the magnitude squared, right, so we're essentially finding what's the probability of finding any state that encompasses this wave function over all space. It has to be equal to 1. If this particle exists, we have to be able to find it somewhere in space. So when we expand this out, and again, I'm just going to do indefinite integrals, or I'm just going to drop the limits, and I'm also going to drop all the stuff in the parentheses for the wave function from now on. So now we input what we have. Okay, now so we can go ahead and pull this constant out. Since we know it's a real constant, we can drop the absolute value signs for that. And now what we're left with is the magnitude squared of this stuff in here. However, since we're dealing with wave function, it's not as easy as squaring it. To find the magnitude of it, we have to multiply by the complex conjugate. Oops. There we go. And we're going to go ahead and just do this more explicitly by foiling it in. Should be pretty quick. Let's see here. We got a 9. All right, nice work, everybody. So as you can see, whenever these limits and the integration comes in and actually does on each one of these constituent little linear combinations here, these two that I just pointed to right here, these will become 0 because the overlap between these two orthogonal states actually right now are 0. So the only thing that survive are these, and these become zeros once the integration happens. So let's go ahead and let that happen. As you can see, this is all shaping up to the same thing that I showed up here. So now whenever we go ahead and solve for a squared, it's 1 over square root of 25, which of course equals 1/5. And that is our normalization constant, the coefficient needed to make sure that these probabilities, whenever they are summed up after you take the square magnitude, equal to 1. The probability of finding the particle anywhere in space has to equal 1.